In this topic, we're going to be talking about something called the law of sines. But the law of sines doesn't apply to just any old triangle. First of all, notice that the triangles I have drawn here are not right triangles. But that's okay. I'm going to explain how we use right triangle trigonometry to justify using non-right triangles. Believe me, there's still right triangles involved. But the law of sines is only going to apply under certain conditions. And so before we begin, I want to take a moment and talk about the different ways in which you can combine sides and angles to get three different parts to a triangle. And then we'll talk about which of those cases we can use the law of sines for, and for which we need a different approach. One of the things we can have three of in a triangle is sides. If we have all three sides, if we know the lengths of all three sides of a triangle, we tend to call that the side, side, side case. If we know all three angles, we're going to call it the angle, angle, angle case. That would be A, A, A. So that's those two cases. You either know the lengths of all three sides of a triangle or you know the measures of all three angles. What if you knew two angles and a side? Or what if you knew two sides and an angle? Those are the only other combinations that are possible. Now you can either know two angles and a side, or you can know two angles and the side in between them. And by that, I mean this. What if you knew two angles and the included side, the side between the two angles? What if you knew two angles and the side, or one of the sides, not included between those two angles? On the other hand, what if you had two sides and an angle versus what if you had two sides, sorry, I put the wrong color pen here, two sides and the angle between them? So you can either have two sides and one of the angles not included between those two sides, either that one there or this other one over here, or you can have two sides and the angle between those two sides, the included angle. Now, what's the point in going over all of these different cases? The point is that if you know the lengths of the three sides of a triangle, then you know the only triangle that can be made up of those three sides. You could have another triangle exactly the same size, but you can't have a triangle with a side length of this side and a side length of this side and have a different side length of this side. If these two side lengths are fixed, then the third side length must be fixed as well. There's only one size of triangle, one triangle with multiple copies of that triangle that has these three side lengths. Also, you could flip the triangle or rotate it, but the side lengths don't change. In other words, we would say that this is a unique triangle. There's no other way you could combine these three side lengths and make a different size of triangle. The three angles case, on the other hand, if you have a triangle of this size and a triangle of this size, and the angles are the same size in both cases, then these are not unique triangles. These two angles are the same size, these two angles, and these two angles are the same size, yet the triangles are different sizes. So in the angle, angle, angle case, we cannot determine a unique triangle. If I give you the right pieces of information, you can figure out the other three pieces of missing information for this triangle. You can figure out the three angles here. Let's put those in pink. If I give you the green information, you can figure out the pink information. But you can't do that in the angle, angle, angle case. You don't get a unique triangle here. You can figure out the missing pieces of an angle, angle, side. If I give you two angles, you can figure out what the third one must be. And once you have three angles, as long as you have one side, you can also figure out what the other two sides are. If you have two angles and one side, which is the case we just talked about, but the angle is, the side is included, well, that's another case where you can figure out the third angle and the other two sides. In the case of a two sides and one angle triangle, you can figure out the third side, and you can figure out the two missing angles. Now, how you do that, we haven't talked about yet. We're going to be talking about some of these when we talk about the law of sines, but we're not going to be talking about, oh, what color should I use now? Maybe yellow. We're not going to be talking about the angle case at all, because we cannot determine a unique triangle if all we know about the triangle is its three angles. If we know two angles and a side, then yes, that's a unique triangle. The only way we can come up with a different triangle in this case is if the triangle is an exact copy of the one that we're going to find. If you know either two angles and a side, or two sides and the non-included angle, any of these can be solved using the law of sines. What I mean by solved is the same thing as I meant by solving a triangle back in the first unit in the textbook. When you know some of an angle, some pieces of information about a triangle, and you're looking for the other three pieces of a triangle, then we call that solving a triangle. You can solve these three triangles by using the law of sines. For the other two cases, we'll need the law of cosines. We're not quite ready for that yet. That's in the next section. But all of these can be solved if you know certain pieces of information. Then you can find the other pieces of information using the law of cosines in these two cases, and using the law of sines in these three cases. We'll talk about these two cases first because they're fairly straightforward. This last one, in terms of the law of sines anyway, that one's a little bit more complicated. So we'll deal with that one in a separate topic. All right, let's talk about what the law of sines actually is. Okay, here's a triangle. I've labeled the sides A, B, and C, and I've tried really hard to make it look like it's not a right angle, not a right triangle. But if I drop a vertical, I say vertical, I actually mean perpendicular. It may not be a north-south line. It may not be perfectly straight up and down, but it's perpendicular to the base there. Then I've actually formed two right triangles. Even though the overall big triangle here is not a right triangle, these two are. Let's go ahead and label that altitude there H for height. Now we know something about the height because we learned a formula for the area of a triangle, regardless of whether it was a right triangle and regardless of its size. We learned that the area of a triangle is equal to 1/2 AB times the sine of C. Let's label the angles here now as well. Remember that traditionally we say that the angle across from side C is angle C, and the angle across from side B is angle B. So that leaves this one as A. Now when I say that the area of the triangle is 1/2 AB sine C, remember that the C angle right here is included, right? It's the angle between A and B. I can't say that this is A and this is B and that this is angle C over here. That won't work. It has to be the included angle, which is why we get away with writing the formula the way that we do. So here we've got the included angle C between A and B, sides A and B. Let's write that formula for area a couple of different ways. We can write it as 1/2 BC sine A and 1/2 AC sine B. B is the angle included between sides A and C. B is between A and C. And A is between B and C. A is between B and C. So I can use any of these three formulas to represent the area of this triangle, but they're all this triangle. It's all the same triangle. So that means that this area, let me use a highlighter here. This area is the same as this area And that's the same as this area. And that means that all three of those things are equal. So that lets me write 1/2 AB times the sine of C is equal to 1/2 BC times the sine of A, and that is equal to 1/2 AC times the sine of B. If you look just at this, the first two of these, if you imagine this equality written down on a piece of paper and you multiplied both sides of the equation by 2, it would cancel the 1/2s. If you imagine these two being written down and multiplying both sides by 2, it would cancel these 1/2s. So I can multiply all three so-called sides by 2 at once, and I get AB times the sine of C equals BC times the sine of A equals AC times the sine of B. Now I'm going to take all three parts of my equality, all three parts of my equation, and divide by A, B, and C. A, B, and C. In the case of the first expression, the A and the B cancel. In the case of the second expression, the B and the C cancel. And in the third one, A and C cancel. And so that means the sine of C over little c, side C, and the sine of B, well, we've got A next, let's go ahead and stick with that. A, sine of A over the side A, and the sine of B over the length of side B, those are all equal as well. And this is what we call the law of sines. That's it. Usually, you only pick two of those to work with at any given time. The point in having all three of them is it sort of sends home the point that it doesn't matter which two sides and which two angles you're working with, the law holds. Let me show you what I mean. Here are the two cases in which we can use the law of sines. Angle, side, angle. And you can tell from this that the side is sandwiched between the two angles. It's even in the notation. The side is sandwiched between the two angles. And side, angle, angle. If you pick a side, this one here is 5 feet, and then from there you go to the nearest angle, and then the next nearest angle, you'll have this 5 feet, this angle is 100 degrees, and the next angle over is 27. So the notation even tells us what order to go in. Now, I don't expect you to memorize that angle side angle is law of sines and side angle side is law of cosines. I don't care about that. I'll show you how to tell from a diagram or from the information given to you in a problem whether it's appropriate to use the law of sines or whether it's appropriate to use the law of cosines. My point is that there are three cases in which the law of sines is appropriate, and one of those is the topic of the next video, but the other two we're addressing here, and those are angle side angle or side angle angle. If you have two angles in a triangle and the included side, or two angles in a triangle and one of the non-included sides, then you can use the law of sines. All right, let's take a look at the problem on the right-hand side of the screen first. And I'm going to start by reminding us what the law of sines says. It says that the sine of an angle divided by the length of the side opposite that angle is equal to the same ratio for either of the other two angles. It's sine times the length of the side opposite. And it doesn't matter which angles we call A and B and C, so let's go ahead and label a couple of these. We have both angles, so I'll call this one A and this one B. And since the given side is opposite angle A, that's going to make that side A. And with that, I can fill in my formula. I have the sine of an angle A, which is 27 degrees, over the length of side A, which is 5. That's equal to the sine of angle B, which is 100 degrees, over the length of side B. And I don't know that one. I don't know the length of side B. In fact, I know everything but that. Now, I have 3 out of 4 pieces of information. So all I have to do now is solve algebraically for B, and I'll know what the length of side B is. Let's go ahead and label side B. It's here. All right, to solve this problem, I just need to cross multiply. That's not my favorite terminology, but I know most students are comfortable with it, so I'll go with that. 5 times the sine of B 5 times the sine of 100 is equal to b times the sine of 27. Those are in degrees. I'm solving for b, so I'm going to divide both sides by the sine of 27. Notice that I have left my problem all in terms of sines. I haven't taken the sine yet because these are not friendly angles. I'm not just going to be able to pull them from a table, and I'm not going to be able to give them as exact values. So I'm leaving them in that form and pretty much until the last minute, because it's only then that I'll need to put them into a calculator and I'll get a decimal. The calculator will keep the decimal as accurate as possible for the longest amount of time possible, leaving me with the most accurate answer. So what I have here is that b is equal to 5 times the sine of 100 degrees divided by the sine of 27 degrees. And the rest is calculator work. When I put 5 times the sine of 100 divided by the sine of 27 into my calculator, making sure it's in degree mode first, I get b is equal to 10.8461. I don't know why. It was years ago. I got into the habit of rounding everything to 4 decimal places, and it's a little overkill, but I feel like that's really pretty stinking accurate for a lot of things that we need to do. If I'm told I need 5 or 6 decimal places, then of course I'll do that. But as accurate as I can be without going completely crazy, I think 4 decimal places is enough. This is of course not equal to 10.8461. It's approximately equal. So I'll make that little correction. And then what we have here is the length of side B. So let's go ahead and label it. I'll just put 10.8 for now. Now, that was great. That was our first actual practical use of the law of sines. But depending on what information you have and what you're actually looking for, that may not be enough. For example, I may actually have wanted the length of side C, in which case I can't find it directly, but I can do this much. Or I could find the third angle, and then I could use the law of sines to find my side C that way. So let's go ahead and finish solving this triangle. We have found our first missing piece, and that was side B. It's actually easiest if you have any two angles, to find the third angle. It's probably easiest to do that first. My 3 angles are 27, 100, and let's see, I've got A and B, so this is angle C, and those all have to equal 180 degrees. So if I subtract 27 and I subtract 100 from 180 degrees, I get 53. So now I know how big this angle is too. C is equal to 53 degrees. Well, that was easy. But now notice that I could use the law of sines again to find angle C. To find side C. I know that the angle C is 50 degrees, and I have this opposite, an angle and a side opposite each other, one of which is missing, right? I have angle C, but I don't have side C. And then I have a matched pair in A, right? I have a known pair and a pair with one piece missing. That's how I determine whether I'm going to be using the law of sines or not. I don't have it memorized this way. Let's cordon this off. And let's use the law of sines again to find side C. I know that sine A over A is equal to sine C over C. That means that the sine of 27 over 5 is equal to the sine of 53 over little c, and I don't know what that is. But that's 5 times the sine of 53 equals c times the sine of 27. Dividing both sides by the sine of 27, I get 5 times the sine of 53 over the sine of 27. Notice I'm including my degree symbol even though I'm not saying it. That's going to be what gives me little c. And my calculator tells me that c is approximately 8.7957. So now I have an approximate length for side C as well. Let's go ahead and label it on the triangle. 8.8, I'll call it. 8.8. Now, let's make another observation. This is going to come in really handy in the next topic. Notice that I have a given side of A, which is 5. I found a side which is about 11, and I have another found side of about 8.8, or almost 9. So I have a 9, a 10, and a 5. In order, that's 5, 9, and 10. 5 is the smallest, 10 is the biggest, 8.8 is the one in between. Now, across from the side that's 5 feet long, I have an angle that's 27 degrees. 5 feet's the smallest side, 27 degrees is the smallest angle. 10.8 is the longest side, and 100 degrees is the biggest angle. In between, 8.8 is the middle side, and 53 is between 27 and 100. So as the sides go up, the angles go up to match, or the bigger the angle, the longer the side opposite it. Now, that's just kind of a well-known fact from geometry, but it's worth remembering, it's worth reviewing here because it's going to come in handy pretty soon. All right, let's take a look at our other example here. This one's a little bit trickier, which is why I saved it for last. We have two angles and the included side. So according to the previous screen, we can use the law of sines here. But for the law of sines, I have to have two known things across from each other. I have to have a known side and a known angle, a known side and a known angle, a known side and a known angle, and I don't have that here. But what I do have is two angles. So that means I can find the third side, and then I'll have a known side and a known angle across from each other. And then I can use the law of sines. So in this case, I have to find this third angle first, and then I'll be able to use the law of sines. Let's see. I'm still in degrees, so I get 51 plus 96 plus, I guess I'll just call it C for right now, is 180 degrees. And when I subtract 51 and 96 from 180, I get 33. So that means this angle here that I didn't previously know is 33 degrees. Now I have an angle and a side opposite, both of which I know the measurements for. So now I can use the law of sines. Let's go ahead and label our triangle. If I call this angle A, that makes this side A. And then I think I'll just call this angle B, which makes this angle C. It also means that this is side C, and this right here is side B. Now, I found all three angles, so I've actually already done the part that I did over here second, right? I found my side B first, and then I went and found angle C so that I could find side C. I've already found my third angle this time, so it's just down to finding sides B and C. So I have the known sides, the known quantities, opposite quantities are A. So I'll start with that. I'm going to have the sine of A over the side length A equals the sine of B over the side length B. And then I'll do the sine of A over A equals the sine of C over C. Plugging in my values, I get the sine of 33 degrees over 3 equals the sine B, 96, sine of 96 over side B, which I don't know. 3 times the sine of 96, I'm just cross multiplying, equals B times the sine of 33 degrees. And dividing both sides by the sine of 33 degrees, I get B is equal to this quantity here, which I'll do on the calculator. My calculator tells me that's equal to, or approximately equal to, 5.4781. And that's in centimeters. It's just occurred to me that I very carefully used all my degree symbols over here, but I didn't use any labels for my lengths. Let's see, I have 5 feet is the only given length, but that means that all of these other lengths are also in feet. I'll use the tick mark symbol because it takes less space. I don't have a lot of space here. B is 110.8 feet. There we go. And on this side over here, I'm in centimeters. So now that I've found the length of side B, I know that it's in centimeters. Let's go ahead and label the diagram as well. I have 5.5 centimeters. And now that I've found side B, I can carry on and find side C. That's what this down here is. This gives me the sine, A was 33, the sine of 33 over 3 is equal to the sine of 51 over, C, that's the one I don't know. Cross multiplying, I get 3 times the sine of 51, is equal to C times the sine of 33. Divide both sides by the sine of 33. And you get that C is approximately equal to 4.2807 centimeters. So up here, I'm going to say 4.28. I'll just use 4.3. And there you have it. That's the law of sines. It's fairly simple and straightforward. The only catch is that if you have 2 sides at an angle, this is the case we haven't talked about yet. If you have 2 sides at an angle, then there's something else you have to take into consideration. So we'll take a look at that in the next topic.